Hello, welcome back. So good to see you again. In the previous video, we went through somewhat quickly a few of the common methods in solving ordinary differential equations, and in this video we will implement a superclass and a few of them in Python by building some sort of class hierarchy. So what we'll be employing now to much benefit is object-oriented design, which is very useful, as you will see. So here we are in Python. In order to get started, we need to import some stuff. We need numpy, SMP, and that's it. And we will define a class called ODE solver, which will be our superclass. So we'll just write that down. ODE solver superclass. And we need a constructor, the init method. And the only thing that we need to supply to our superclass is the right-hand side function of the ODE. So just remember that our ODE looks something like this, that we have a derivative on the one side, on the left-hand side, and a function which may be dependent on the solution and of our time step on the right-hand side. And we also need some sort of zeroth solution value. So that's our form that our equation is on. So the constructor needs this function, which must be some sort of callable function. All right? And we'll also define set initial conditions method, u0. Just edit that up there. And because this can either be one single scalar ordinary differential equation or a system of equations, that's why it's called conditions, because there might be several equations, right? So first we'll check if is instance, if we are dealing with just a single number, right? So if this is an integer or a floating point value, we will, now we have a scalar ODE, and we can set the number of equations, which will be important, number of equations to 1. And we will cast this u0 as a floating point number, like so. And if we don't have an integer or a float, we are dealing with a system of equations. And then we say that u0 is a numpy array as array, like so. I think that's correct, yeah. And we'll say that self.number of equations is equal to the size of this array. And we'll lastly set u0 to, well, the inputted u0 up here, because then it'll be a member of the class, right? Okay, what we'll also need, we need a solve method, which will take in a set of time points as input, and we'll say that np will cast these to an array. Yeah, just time points. There you go. And we'll also put the number of time points in a variable called n. So we know that's how long our time loop will have to keep going until we stop. Our solution will store in a u, which will be just zeros to begin with, in the size of n, which is the number of time points. So that's the number of rows, and the number of columns will be this number of equations. So if we have a set of differential equations, then we can store all the solutions. And our self.u, the 0th time point, will be the initial condition that we got from up here, which need to be set before we start, or else it'll just be 0, because this thing doesn't exist, so we will get an error. And then we can integrate or solve, or whatever you call it, the time loop. So integrate. So for I in range n-1, because we go k plus 1 at each time step, so we cannot go all the way to n, we will say that self.I equals I. So we'll keep this time step, and then we'll go self.u I plus 1 equals self.advance. So if we were implementing a specific ODE solver algorithm now, we would write down the code for that here. But we are going to implement these specific methods in different classes, and so the only thing that those classes need to do is to implement this advanced method. So we'll just keep it like that now. And we'll keep going, and then until we're done, return self.u. So we'll return self.u and self.t. That should be it. The only thing that we are missing in this superclass is the advanced method. And we'll write a little note here that advance solution 1 time step. And this needs to be implemented for the solver to work. If it isn't, we will raise a not implemented error there. And that should be it, really. Now we have the beginnings. So now we can implement another class called ForwardEuler, because we're going to implement the ForwardEuler method. And the ForwardEuler class will inherit from the ODE solver, like so. And the only thing we need to implement is the advance method. So now we have U that we need, and an F, and an I, and a T, self.u, self.f, self.I, and self.t, which will be available to us once the solve method has been called and everything is properly set up. And we'll compute the dt, which we have defined before, which is simply the difference between the two time steps we are at, or the next one and the current one, like so. We will return, so now we only need to return the so this is the actual ForwardEuler algorithm or code that goes here, because that's what we need to supply to the solve method up here, right here. This is what needs to go out. You can check in the previous video if you don't remember the ForwardEuler method, but it is. So we begin with the current solution at point I. Could have been k, as we have been writing, but whatever. We multiply time step with the right-hand side function f evaluated at the current solution and the current time step. So because this could be a system of equations, we write this a little bit here and include all the columns, and likewise here. But the time array is only one-dimensional, so we only need the I there. So let's also implement the most common method, which is the Runge-Kutta fourth order Runge-Kutta method. Runge-Kutta 4. We just call it that, and it needs to inherit from ODE solver. And the only thing we need to implement is advance. Here we also need the solutions, the right-hand side function, the step we're at, and the time array, which we get from self.u, self.f, self.I, and self.t. So the same thing so far, right? But here, because this is a more sophisticated method, we have to do a bit more. The time step is still the same, just like up here at the ForwardEuler method above. We have ti plus 1 minus t of I. That's the same, exactly the same. We also compute, well, we call it dt half or dt2, because we need half a time step as well. So there we simply do this. Like so. And then we need to compute all the k's, which you might or might not remember. You could look them up or check in the previous video. But k1 was dt times f of u of k, and we need all the rows, all the columns, sorry, and evaluated at t, of I of I. So that's k1, k2. It's somewhat similar. It's f evaluated at u of I plus 0.5 or a half times k1, and it needs to be evaluated at a time point as well, which is t of I plus half a time point, which will be this dt2 up here. Okay, we need 2 more k's. K3 is almost the same as this, so I'll just copy it. There you go. But here, instead of multiplying with k1, we multiply with k2. And that's the only difference there. And then we have a k4, which is dt, the f here as well, u, I, at all rows, plus k3 at t of I plus dt. So that's it. And then the last step, which actually provides us with the next step in the solution, we write return u, so this is the current step, like so, plus, and then 1/6 times k1 plus 2 times k2 plus 2 times k3 plus k4. And that's it. That's it. It's a bit more tricky, but it should provide a somewhat better result. But of course, with a more sophisticated method, there's more to be done. There are more flops, floating point operations, but the gain in accuracy or precision is usually much better. So this is which is why the Runge-Kutta, the fourth order Runge-Kutta is so popular. All right, so that's it for this video. I think in the next one we need to test these solver classes on a problem, and we'll also write a problem class to see that you can actually define a problem in a very nice way as well. So yeah, we'll solve a few exponential equations so you see how they work and how they compare the very simple ForwardEuler versus the fourth order Runge-Kutta. See you there.